So now you know all about calculating the determinant for any matrix. Yes? But now we are going to look some properties of the determinant. So this is the final section of this chapter 2.1. So properties of determinant. So the first property is the determinant of a product. What is the determinant of a product of two matrices, A times B? Well, it's equal to the determinant of A times the determinant of B. Okay? And this makes sense if you think about what the determinant means. So the determinant is how areas or volumes are transformed by a linear transformation. So if you apply two linear transformations, one after the other, then the volume is first transformed maybe by 1/2, then by 1/3. So the total volume when you combine both would be scaled by 1/2 times 1/3 equals 1/6. Yeah. So you just multiply the determinants of the different matrices that form the chain. Notice that this would mean that the determinant of A times B is equal to the determinant of B times A, even if they are different matrices, which is interesting. Okay, the next property will be the determinant of the transpose. And what I mean here is that the determinant of the transpose of a matrix is equal to the determinant of the matrix without transpose. Okay, so transposing a matrix does not change its determinant. This is very important because it means that anything that we say about the columns of a matrix when we talk about the determinant will also be true about the rows of the matrix. Yeah, because it doesn't matter if you look at columns or if you look at rows, the determinant is going to be the same. Okay, next property is the determinant of the complex conjugate. So the determinant of the complex conjugate of a matrix is equal to the complex conjugate of the determinant. So you can take the complex conjugation outside. Okay? Very well. And finally, we are going to talk about the linearity of the determinant. So first thing, determinant is not linear with the matrix, or is not a linear operation. So the determinant of alpha A plus beta B is not equal to alpha determinant A plus beta determinant B. Okay? It's not equal to that. So it's not a linear operation. However, the determinant is linear in the columns. And what do I mean by that? Let me write it explicitly. So this means that the determinant of a matrix, and let's say that this matrix has a column A, and then it has a column that is alpha B1 plus beta B2. Let's say that this is the second column, for example, and then it has another column which is C. In other words, one of the columns of the determinant is a linear combination of vectors. Yeah? And here I chose as an example the second column, but it could be any other column. Then this is equal to alpha times the determinant of a matrix given by this, B1, C, plus beta times the determinant of a matrix given by A, B2, C. Okay? So basically the determinant is linear whenever you do a linear combination in one of the columns only. Okay? So for example, this means that as a product of this property, or as a result, you can see that the determinant of a scalar times a matrix must be equal to the scalar to the power n times the determinant of the matrix. Why is this? Because if you scale a matrix times alpha, that's like scaling every single column. Yeah? How many columns? N columns in general, when n is the size of the matrix, of the square matrix. Therefore, if each of the columns has been multiplied by alpha, you can apply the property that the determinant is linear in the columns. So you need to multiply the determinant by alpha n times, one for each column. And therefore the determinant of alpha times A is equal to alpha to the power n times the determinant of A. So this is a result of the previous property. Next, we are going to look at some properties of the determinant, but related to the columns of the matrix. So just by looking at the columns, you can say a lot about the determinant of a matrix. So let's see that in the next video.